So this is a worksheet of problems dealing with, well, cylindrical and spherical coordinates and trying to find essentially volumes, but some other things with triple integrals here. So the first question, we want to find the volume of the part of the cylinder x squared plus y squared less than equal to 3 that is inside the ball x squared plus y squared plus z squared less than equal to 4. Here. So first thing we're going to do is get a picture of what's going on. I'm going to use Mathematica here to get a better sense of that. So what we've got here is we have this cylinder, is sort of this vertical part, maybe it's kind of hard to tell, and then this bulging out part is the sphere, or the ball here. So there's the top of the sphere. You can see the bottom of the sphere. And what we're looking for here is essentially the solid here that's sort of, well, what happens when you would take this cylinder and sort of cut down on the sphere. So basically it's the sphere, but you're cutting off sort of this bulging part outside of the cylinder. So a picture of just the part we're looking for is right here. And I've got these green and blue circles. It's the circles of intersection, one on top and bottom, just so you can kind of see what they'd look like on this figure here. So this is the solid whose volume we're trying to find. So you've got sort of this cylinder side and then these kind of domes on the top and on the bottom here. So if we try and draw that here, I mean, essentially here what I've got here, I'm going to just kind of draw this and maybe think of it as sort of an xz plane, knowing I can rotate around the x to get the y here. So I'm going to kind of draw a two-dimensional picture here. Essentially, I've got a circle. This is of radius 2. That's our sphere, x squared plus y squared plus z squared equals 4. Less than equal to 4 would be the ball. Sphere would be equals to 4. So that was this thing, essentially, is that. And then let's maybe go to red and look at x squared plus y squared. We could do equals 3. Well, since I'm sort of fixing the x and not doing the y, what I'm going to look at is this is a circle, or maybe a cylinder, of radius, it's going to be square root of 3. So out here somewhere at square root of 3, which is like 1.7, so a little less than 2, there's going to be this cylinder that goes up, and then that would rotate around. So over here somewhere you're going to get sort of the other half of the cylinder, and then you get sort of a circular, well, when it rotated, you'd get a circular kind of region here. So we're looking for the volume in between here. So when I look at this picture here, what I'm going to look for is, should I do cylindrical coordinates, spherical coordinates, something else? This one, the probably easiest thing for me here is if I look at this straight from the top, I get a circle here. And that kind of makes me think cylindrical coordinates is going to work. So I sort of have circular cross sections that are all the same sort of radius in the middle, and then some other circulars here. But sort of that shadow is really this circle here. And that means cylindrical should work. We'll do r and theta sort of define that shadow of a circle, and then z is going to go from sort of this bottom dome to the top dome here. So the way that's going to work in, let's do cylindrical coordinates here. So our integral, okay, we wanted to integrate 1, but we need our Jacobian, that's r in cylindrical. And then I'm going to do the order dz, dr, d theta. I basically want to have z first because I'm going to think about in my picture here that z goes from some bottom function of r and theta to some top function of r and theta here. Actually, it's just going to be r. But z does that, and r and theta, to define this circle, just have sort of constant ranges. So r is going to go from 0 to square root of 3, which is the radius. Theta is going to go from 0 to 2 pi to get 1 full revolution here. So my bounds, here, let's see, theta, that's 0 to 2 pi. I'm rotating it all the way around. R is going to go 0 to square root of 3. So that circle, cylinder, is radius square root of 3. Now, z, I went from negative, well, yeah, so we're going to go from negative of the bottom of this sphere to the top of the sphere. And so I want to write those equations, the sphere equation, in terms of r and theta. So that sphere equation is x squared plus y squared plus z squared equals 4. Whoops, let's clean that up a little bit. So we have x squared plus y squared plus z squared equals 4. And in cylindrical, x squared plus y squared is r squared. So I can take x squared plus y squared, write that as r squared plus z squared equals 4. And I'm trying to solve for z, so I get z squared equals 4 minus r squared. So z is plus or minus the square root of 4 minus r squared. So the bottom bound is negative square root 4 minus r squared. Top bound is square root 4 minus r squared, the positive square root. So that sets up an integral that should give us the volume of this region in cylindrical coordinates. Now we need to evaluate this. So first bit, I need to integrate r with respect to z. I get an integral from 0 to 2 pi, integral from 0 to square root of 3, and then r integrates to rz. And then my bounds, my bottom bound of z is negative square root 4 minus r squared. Top bound, whoops, let's write the z equals positive square root 4 minus r squared. And then I have to do dr d theta still. So let's just continue this integral down here. I get an integral 0 to 2 pi, integral 0 to square root of 3. I'm going to plug in z as square root 4 minus r squared. So it's going to give me r times square root 4 minus r squared. And then I'm going to subtract, when I plug in z, as negative square root 4 minus r squared. So subtracting a negative gives me a plus, and I'll get r times, again, that square root 4 minus r squared. And then dr d theta. So let's maybe go down a bit here. Now what I notice here is I have r squared of 4 minus r squared, and then another r square root 4 minus r squared. So I can combine those together, so I only really have one integral to do instead of two, I guess. But I get 2r square root 4 minus r squared, dr d theta. And I need to integrate this 2r square root 4 minus r squared with respect to r. So I'm going to do that by u substitution. I'm going to let u be 4 minus r squared, and then du is going to be negative 2r dr. And I've got the r outside already, actually 2r, so that will work out just fine. So what I'm going to do is maybe I'll go off to the side here. Let's maybe do this in green here. Is I'm going to do an antiderivative of 2r square root 4 minus r squared dr. I'm going to let u be 4 minus r squared, thing under the square root. And then du is negative 2r dr. And so my integral, let's maybe draw an arrow there. My integral is going to be I have a square root u, negative 2r dr. I've got 2r dr. I'm missing the negative, so I'll get a negative, let's write that a little cleaner. I'll get a negative square root u du. And so that will give me negative u, square root u is u to the 1/2. Integrate, I get to the 3/2. Divide by 3/2. Divided by 3/2 gives me a negative 2/3. U is 4 minus r squared to the 3/2. So there's sort of my antiderivative there. And so what I get when I plug that in here is I get 0 to 2 pi. I get the negative 2. Let's just put the 4 minus r squared to the 3/2 in the numerator and put the 3 in the denominator. And we go from r equals 0 up to r equals square root of 3 d theta. And then we just need to evaluate that. So we get 0 to 2 pi. When I plug in square root of 3, I get 4 minus square root of 3 squared is 3. 4 minus 3, that's 1. 1 to the 3/2 is 1. And then minus a negative gives me plus 2. When I plug in r equals 0, I get a 4 minus 0. That's 4. So I get 4 to the 3/2. But square root of 4 is 2. And then I raise to the 3rd power to do the 3/2. That's going to give me an 8 over 3 d theta. And so now I get an integral from 0 to 2 pi. Let's see, this is 16/3 minus 2/3. That's 14/3 d theta. So to integrate this integral 0 to 2 pi, 14/3 d theta, what we're going to need to do is, well, we integrate 14/3 with respect to theta. That gives us 14/3 theta, where we evaluate from theta equals 0 to theta equals 2 pi. Plugging in the 2 pi gives us 14/3 times 2 pi. Plugging in the 0 gives us 14/3 times 0, or 0. So really that second term drops out as a 0. And we end up with 28/3 pi. So that's the value of our integral here. So we found the volume of the region to be 28/3 pi. That we did that with a cylindrical integral. Now we can also do this integral as a spherical integral. So let's go back and look at the shape again. So here's our general shape of what's going on. So again, we've got sort of a cylinder with sort of a dome on top and a dome on the bottom. Now to do this in spherical, one thing I'm going to do first of all, I'm going to sort of only worry about the top half. So what I'm going to get here is that really my volume here is 2 times the volume of the top half. So this is the part where z is greater than or equal to 0. So we're just going to worry about that first. And then we just have to set up bounds in spherical coordinates. And so what you've got here, so let's just go back and draw sort of our picture again, is if you have sort of a z-axis, and then this is maybe an x or a y or an r, we've got a circle of radius 2, and then there's this cylinder here that really goes up like this here, and that's at square root of 3. So sort of negative square root of 3, negative 2 here. Well, when we do spherical coordinates, we have 3 sort of variables here. One of them is theta. Theta is going to go 0 to 2 pi because this wraps around all the way. So let's maybe set up our spherical coordinates. Theta goes 0 to 2 pi. That means we get a d theta on the outside. Now what we want to integrate is the function 1, but our Jacobian when we switch to spherical is rho squared sine phi. And I'm going to do this as d rho, d phi, d theta. So our theta went from 0 to 2 pi. Now phi is a little bit interesting. Maybe not phi, but the combination of phi with rho here. And that's because rho starts at the origin, really, and sort of goes out. Now this is in 3-dimensional space. And should go out until we hit sort of a surface. But if you look at this red sort of arrow, the surface we hit is that sphere, which shows up as the sort of a circle in this diagram. If we look at maybe this sort of cyan colored, let's pick a different, let's pick maybe just a straight up green here, so sort of a bright green. Let's try that. So if we pick a bright green and we go this way, we're going to hit, well, there we hit the sphere, but we already hit the outside of our actual shape here. This is at the cylinder. So what we want to do, this is probably not going to work so well. So let's maybe redo this. Whoops. Let's see if we can precision pull out just the green. So what we do is we start at the origin, and we're going to end up at the cylinder. And sort of the splitting mark here is going to be right here, sort of that intersection here. So what we need to do, a couple things here. One is I'm going to try and build a triangle. Let me do this in black here, where I take this sort of splitting bit, and then I go over. I want to look at that triangle. And I particularly want this angle here. That's my phi. So my phi is going to start up at z and sort of go down to that point, and then we'll have a particular rho. And then once we get beyond that point in phi, we're going to have a 0 to a different function for rho. So that means what we're going to get is 2 separate double integrals, or sorry, 2 separate triple integrals. So they'll both be rho squared sine phi. You do both of them as d rho, d theta, whoops, d phi, d theta. You could do it either order, actually. It's kind of ugly there. Let's try again. D phi, d phi, well, I'll just leave it. D theta. So theta again will go 0 to 2 pi. Now what we're going to get is our phi here. The first one I'm going to start at 0 and go down to whatever this angle is. And we'll draw that angle in orange. So that angle there would be the phi. And so what I'm going to get is in the first integral, I'm going to go from 0 to whatever that sort of mystery angle is. In the second integral, I'm going to start at that angle and go down to pi over 2. Now, and then rhos, I'm going to go 0 out to, this is the sphere. So that sphere was a sphere of radius 2. So that's going to be 0 out to 2. So the radius is 2. That's x squared plus y squared plus z squared is 4. That's rho squared is 4. Rho is 2. The other thing where we go from 0 out to, we've got to find this cylinder function as a function, well, write it as rho as a function of phi and theta. Theta won't show up, it'll just be phi here, turn out. So that's really our setup. And the other thing I left off was this multiply by 2 because we were sort of only doing the top half. So there's our general setup here. And we got a few things to fill in here. So we've got a few unknowns here. So let's worry about this phi first. So that black triangle, when I look at this, there's phi. That's sort of our question mark, what we're looking for. What we know here is this hypotenuse. That's a radius of the sort of big sphere. So that's 2. This height here, well, I don't know what that height is, but I know what it is the height of the intersection of the sphere and the cylinder. So in Mathematica's sort of view, it's really the height of this green circle here. Or if we go back up a bit further, here, so that's that green circle, that's where this cylinder, which is part here, intersects this sphere. So you can kind of see the green a little bit there, but that's what we're looking for. So the green, here, what we can do is we can go and say that green has to satisfy both the sphere equation, that was x squared plus y squared plus z squared equals 2, and it has to satisfy the, or not 2, equals 4, radius 2, and it has to satisfy the cylinder equation, which is x squared plus y squared equals 3. Now what we're trying to do is really find the z. We want to get sort of the z height here. So what we can do is plug in x squared plus y squared equals 3 into the first equation. Put these together, you get 3 plus z squared. So this x squared plus y squared in this first equation gets replaced with the x squared plus y squared in the second equation, which is 3. So that equals 4. That gives us z squared equals 1. And so z is plus or minus 1. And so if you go to the picture here, you get sort of the circle on top, or sorry, this green circle is going to be z equals 1. The sort of light blue circle is going to be z equals negative 1. So what we get in our triangle is we get a 1 as sort of the leg next to phi. And what that means is we're looking for an angle whose cosine is 1/2. So at this point, cosine phi is 1/2. And that means phi has to be, that's going to be pi over 3. And so what that means, here's we can go up and replace these question marks with the angle pi over 3. Here. Okay, let's go and look at what this, or see what this looks like in sort of a nicely drawn version. So here I've got a little bit of a setup. This is when I go phi from 0 to pi over 3. So phi equals 0 is the positive z-axis, and then I go down, phi equals pi over 3 is this cone here on the bottom. Here's that same green circle that you can see up here. And I just went from phi equals 0 to pi over 3. So I'd sort of shoot from the origin out and hit this sphere. Any of those places. We can rotate this around a bit. See sort of what that looks like. Now when I go from pi over 3 to pi over 2, this is the part I'll get with that same green circle. Here, so I'll get sort of, I start at the origin and I shoot through this solid, maybe coming at me. I'm going to end up on this cylinder here. So you get sort of a disc on the bottom. It's like a cylinder on the outside. And the idea here is I could put together this shape with this shape would sort of nest in there perfectly, and together they'd form the top half of this. So that's the idea sort of visually of what's going on as you take that shape, and they each have sort of a boundary row that is different. So that's our visualization of what's going on, and, well, visualization with the help of some technology. So now we have to get this last bit we're missing, and that's that cylinder function. So the cylinder, again, was x squared. Whoops, let's go back to the blue here. Cylinder was x squared plus y squared equals 3. Now, in terms of spherical, let me just plug in what x and y are. So x is rho sine phi cosine theta. Do that squared. Plus y is rho sine phi sine theta. That should be squared as well. That should equal 3. And what you get is rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta equals 3. Looks kind of awkward to deal with, But if you notice here, what I've got is this rho squared sine phi, rho squared sine squared phi, and a rho squared sine squared phi there as well. So both terms have that common factor. So I'm going to factor that out, and what's left turns out to be really nice. It's cosine squared theta plus sine squared theta equals 3. Well, that cosine squared theta plus sine squared theta is 1. It's a trig identity. And so we get that the cylinder is the equation rho squared sine squared phi equals 3. Now you can take the square root of both sides. We're going to assume rho is positive. Phi goes from 0 to pi over 2. So sine phi is also positive. So I don't have to worry about negative values here. When I take a square root of both sides, I get rho sine phi equals square root of 3. And what we're looking for, we want to solve this either for rho or phi. The bounds we have on our equation, this is a rho bound going from 0 out to something, which can be a function of phi. So we want to solve the equation of the cylinder for phi. It tells me rho equals square root of 3 over sine phi. Or maybe square root of 3 cosecant phi. So what we can do is we can go here, and this question mark turns into square root 3 over sine phi. Okay, so now we've got the thing we need to evaluate. We just have to evaluate this. I'm going to go and let's see if we can copy this down here. So I'll take the whole thing, edit, copy, move it down here. Whoops, edit, paste. So there we go. Let's just move this up a bit. Okay. And there's a pen. So there's this sort of integral again. This is this volume we're looking for. We've got two integrals, I guess. Well, two triple integrals. So I get 2 times the first integral. I can integrate with respect to rho. I'll get rho cubed over 3. So I get 0 to 2 pi, 0 to pi over 3. And I'm going to get rho cubed over 3. I'm going to do rho equals 0 to rho equals 2. I still have the sine phi. And then I have d phi, d theta. Plus this second integral is 0 to 2 pi. Integral from pi over 3 to pi over 2. I also will get, well, let's put the sine phi out in front. Probably a little more natural. I could have popped that sine phi out in front. And then I'm going to get rho cubed over 3. I'm going to go from rho equals 0 here up to rho equals square root 3 over sine phi. And to do a d phi, d theta. Okay, let's keep trucking along here. Show that there. Okay, so what we get, let's see, we're just going to plug these in. I get 0 to 2 pi, 0 to pi over 3. 2 cubed is 8, so I get 8 thirds. Plug in the 0, I'll just get a 0. So I get 8 thirds sine phi, d theta, plus, let's see this other one. I'm going to pull, how about the 1/3 out in front? Maybe I could have done that with the other integral as well. 0 to pi over 2, pi over 3 to pi over 2. And let's see, I get a sine phi times, let's see, when we plug in square root 3 over sine phi, we're going to get square root of 3 cubed is going to be 3 square root of 3. Now I'm wishing I hadn't pulled that 1/3 out because then that would just cancel. And that's over sine cubed phi. And when I plug in the rho equals 0, I get 0. I get my d phi, d theta here. Okay, so it's 2 times. Here I'm going to pull the 8 thirds out, integrate from 0 to 2 pi. Sine phi, the integral is negative cosine phi. And that goes from phi equals 0 to phi equals, whoops, starting to think a little bit ahead, phi equals pi over 3. I have to integrate with respect to theta. Plus, this 1/3 I can cancel with that 3. I have a square root of 3 I can pull out in front. Integral 0 to 2 pi. I'm going to leave this as pi over 3 to pi over 2 just yet. Sine phi over sine cubed phi is 1 over sine squared phi. That's cosecant squared phi. D phi, d theta. And let's see, we get a 2. here we have an 8/3, let's see, 0 to 2 pi. And what I'm going to get, let's see, when phi is pi over 3, cosine phi is negative square root 3 over 2. Well, it's square root 3 over 2, but I pick up the negative here. I'm going to get minus when cosine is 0. Wait, no, when phi is pi over 3, got the wrong cosine there. That should be 1/2. When phi is 0, cosine is 1. So I'll get plus 1. That'd be my d theta. Plus, I get square root 3, integral 0 to 2 pi. Now, cosecant squared phi. So I know that the derivative of cotangent is actually cotangent theta, or cotangent phi, would actually be negative cosecant squared phi. This is a lot like the derivative of tangent theta is secant squared theta, except I put the cos in and that introduces a negative somehow. So what I'm going to get is negative cotangent phi. The derivative of negative cotangent phi works out to be cosecant squared phi. So it looks a little bit bad, but it's an identity that hopefully you can recognize. And these bounds would be phi bounds. And so I get 2 times, let's see, 8/3. I'm going to get 1/2, integral 0 to 2 pi. It's actually going to be a positive 1/2 d theta, plus square root 3. I'm going to get integral 0 to 2 pi. Let's say I get cotangent phi. So cotangent is cosine over sine. Pi over 2, cosine of pi over 2 is 0. Sine of pi over 2 is 1. So cotangent of pi over 2 is 0. So I'm only going to get the pi over 3. Cosine is 1/2. Sine is square root 3 over 2. And so that's going to turn out to be 1 over square root of 3 d theta. My square root 3's cancel. And when I integrate 0 to 2 pi with d theta, I'll get a theta. And then essentially I'm going to get theta evaluated at 2 pi minus theta evaluated at 0. Basically, that integral is just going to multiply by 2 pi. So what I end up with is 2 times 8/3 times 1/2 times 2 pi plus really just 2 pi. And so what I end up with, let's see, I get 2 times, let's see, these 2's cancel. I get 8 pi over 3 plus 2 pi. So that's 2 times 8 pi over 3, whoops, thinking ahead probably, 8 pi over 3 plus 6 pi over 3. That's 2 times 14 pi over 3. That works out to be 28 pi over 3, which, as it should be, is the same volume we found using cylindrical coordinates. So we're sort of done with this question. We've done it both in cylindrical and spherical. You really only need to do this in one of those ways. In this particular problem, cylindrical probably worked out to be a lot nicer, a little bit easier to think about. It's probably the way I would do it. But it's nice to go through and sort of do both cylindrical and spherical just to kind of see how both work and kind of get a feel for how they work.